Prove the following by using the principle of mathematical induction for all n belonging to natural number. In this question, we have an equation and we need to prove it by using the principle of mathematical induction. So let's proceed with the solution. Let the given statement be Pn, that is, here we have Pn such that 1 upon 1 into 2 into 3 plus 1 upon 2 into 3 into 4 plus 1 upon 3 into 4 into 5 all the way up to 1 upon n into n plus 1 into n plus 2 is equal to n times of n plus 3 upon 4 times of n plus 1 into n plus 2. In our first step, we will try to verify whether the given equation holds true or not for n equal to 1. Now, for n equal to 1, on the left hand side we have P1 equal to 1 upon 1 into 2 into 3. This is equal to 1 upon 6. Whereas on the right hand side we have an expression where we need to substitute n equal to 1 to get P1. This gives us 1 into 1 plus 3 upon 4 times of 1 plus 1 into 1 plus 2. This is equal to 1 into 1 plus 3 is 4 upon 4 into 1 plus 1 is 2 into 1 plus 2 is 3. So these 4 gets cancelled from the numerator and denominator, and we are left with 1 upon 2 into 3, which is equal to 6. Since we have the same value of P1 for both left hand side and right hand side, therefore we will say that P1 is true. Here P1 is true for the given statement, which will lead us to our next step, that is the assumption step, where we'll assume that P of k is true for some positive integer k. Assume that Pk is true for some positive integer k, that is, here we have Pk such that 1 upon 1 into 2 into 3 plus 1 upon 2 into 3 into 4 plus 1 upon 3 into 4 into 5 and so on up to 1 upon k into k plus 1 into k plus 2 is equal to k times of k plus 3 upon 4 times of k plus 1 into k plus 2. Now let us call it as equation 1. In our last step, that is the generalization step, we will try to prove that P of k plus 1 is also true for the given statement. Now we shall prove that P of k plus 1 is also true. That is, here we have P of k plus 1 is equal to 1 upon 1 into 2 into 3 plus 1 upon 2 into 3 into 4 plus 1 upon 3 into 4 into 5 and so on up to 1 upon k into k plus 1 into k plus 2 plus 1 upon k plus 1 into k plus 1 plus 1 is k plus 2 into k plus 1 plus 2 is k plus 3. And now we have the value of this quantity from equation 1 as k into k plus 3 upon 4 times of k plus 1 into k plus 2. So we'll substitute it and we'll get P of k plus 1 is equal to k into k plus 3 upon 4 times of k plus 1 into k plus 2, and keeping this quantity as such, 1 upon k plus 1 into k plus 2 into k plus 3, and here we can take 1 upon k plus 1 into k plus 2 common from both these terms. So we have 1 upon k plus 1 into k plus 2 into k into k plus 3 upon 4 plus 1 upon k plus 3. In our next step, we'll try to simplify this as much as we can. So here we have 1 upon k plus 1 into k plus 2 into taking 4 into k plus 3 as LCM, we have k into k plus 3 whole square plus 4. This gives us 1 upon k plus 1 into k plus 2 into k times of expanding k plus 3 whole square. We'll have k square plus 6k plus 9 plus 4 as such upon 4 times of k plus 3. This is equal to 1 upon k plus 1 into k plus 2 into k square is k cube plus k into 6k is 6k square plus 9 into k is 9k plus 4 whole upon 4 times of k plus 3. This is further equal to 1 upon k plus 1 into k plus 2 into k cube plus 6k square can be written as 2k square plus 4k square, and 9k can be written as k plus 8k and keeping 4 as such whole upon 4 times of k plus 3. This is equal to 1 upon k plus 1 into k plus 2 into k cube plus 2k square plus k. Well, we can write this k before 4k square plus 4k square plus 8k plus 4 upon 4 times of k plus 3. Well, in the numerator we have k common in the first 3 terms and 4 common in the last 3 terms. So we can write it as 1 upon k plus 1 into k plus 2 into taking k common, we have k square plus 2k plus 1 plus taking 4 common, we have k square plus 2k plus 1 whole upon 4 times of k plus 3. This is equal to 1 upon k plus 1 into k plus 2 into k times of k square plus 2k plus 1 can be written as k plus 1 whole square plus 4 times of again k square plus 2k plus 1 can be written as k plus 1 whole square whole upon 4 times of k plus 3. And now we'll take k plus 1 whole square common in the numerator. So we have 1 upon k plus 1 into k plus 2 into taking k plus 1 whole square common, we have k plus 4 whole upon 4 times of k plus 3. And now we can cancel k plus 1 one time from the numerator and denominator. So we have k plus 1 into k plus 4 over k plus 2 into 4 times of k plus 3. This step can finally be written as k plus 1 into, well, we'll write k plus 4 as k plus 1 plus 3 over 4 times of k plus 2 can be written as k plus 1 plus 1, and again we'll write k plus 3 as k plus 1 plus 2. Therefore, this condition is true for n equal to k plus 1. Thus, we have p of k plus 1 is true whenever p of k is true. Hence, from the principle of mathematical induction, the statement Pn is true for all natural number n. So, this completes our solution. Let us see the next question.